Welcome to Lab 3. This presentation is by Brandon Powell. Let's get into it. In this lab, we will perform a series of experiments to collect data about a bar magnet and its behavior, magnitude, and distance dependence as explained later. We will then compare our real-world findings to a computer simulation through GlowScript. For the experimental portion, we will start by determining the latitude and longitude of our current location as shown here. With this, we can find magnetic north in order to properly account for the presence of Earth's magnetic field in our measurements. In this lab, we will make use of the PHYS-2112 law for magnetic field of a bar magnet and an equation for distance dependence to perform our calculations for the experimental data. Here's a quick look at the setup for the experiments. The picture on the left shows where the magnetometer is on the phone as indicated by the red X. This point will be aligned with the meter stick to allow for more accurate and consistent measurements. The picture on the right side shows our initial reading for the magnetic field. The experiment was conducted outside on a wooden table to avoid any possible interference. By minimizing the X component of the measured magnetic field, we can find magnetic north. This is confirmed by our measured value for the net magnetic field, which is nearly equivalent to our anticipated magnetic field given the current latitude and longitude. Our meter stick was laid out from east to west, and the findings were confirmed with a compass. Now we can conduct our experiment. Part 1 of the lab, as shown in the middle picture, we measure the distance at which our magnetometer reaches certain magnitudes. By accounting for magnetic north beforehand, we can focus solely on variation in the X component of the magnetometer's readings. For part 2 of the lab, shown in the right picture, we find the off-axis distance at which the magnetometer reads a net magnetic field of 100 microteslas and compare it with our computer simulation. We need to save time, so here's Excel. We used it to find a formula. Bam! So here we see the equation we found in Excel. We can use this equation to learn a lot about the magnet, which will help us in the next part of the lab. The relation between the magnetic field, the constants K and N, and the distance value R are indicated by the second equation. It's a lot of natural logs, which is exactly what we use to determine our line equation. This allows us to find the value of the distance dependence N and constant K as indicated here. Now we can use this information in combination with our earlier equations for the magnetic field of a bar magnet in order to determine the magnitude of the magnetic moment of our bar magnet. Pretty neat, right? One item in particular should give us some sense of confidence in our findings. The PHYS-2112 law we discussed earlier had a distance dependence value of -3. Through our experiment, we determined that the distance dependence value was -2.517, which is reasonably close. With this information in our back pocket, we can move into the computer simulation. The table shows our experimental values for distance and the components of the magnetic field. Yellow cells indicate measurements, while other cells are calculations made with these measurements. We then compare this data with the simulation of our experimental setup. Our simulation is done through GlowScript. There's more setup involved for setting the scene of our simulation, but these two pictures show the biggest portions of our code. The left picture shows our function dipole B. This function takes in a value of magnetic moment mu and observation location r and calculates the magnetic field produced. With this function and our experimental values of magnetic moment and perpendicular distance, we can replicate our experiment and calculate the expected values for the magnetic field given these parameters. These are the results of our simulation. The orange and cyan arrows show the magnetic field due to the bar magnet, and the red arrow shows our off-axis point. Notice how the orange arrows are twice as large as the cyan arrows, which matches the way in which the magnitude on axis is twice as much as the perpendicular magnitude. In addition, our red arrow is closer than our viewing distance, explaining why its magnitude is greater than the other arrows. Its direction follows the same behavior we would expect for a magnetic field 45 degrees off of the axis. Below these pictures are our experimental and calculated values for the components of the magnetic field. In a perfectly conducted experiment, these values should be identical, so why aren't they? In our experiment, there are significant forms of interference that are not accounted for in our GlowScript model. We consider the magnetic field of Earth, but there are still numerous other details that can skew our experimental results. Furthermore, when measuring such precise values with mediocre equipment, there's always further room for error. So we will conclude this lab by posing some questions. First, what if the orientation of the experiment did not account for the magnetic north, and the meter stick was placed at an arbitrary angle with respect to Earth's magnetic field? So if we didn't take this into account and we jumped right into measuring with our magnetometer, we wouldn't be able to differentiate the effects of the bar magnet and the magnetic field of Earth. It's critical that we align the setup with magnetic north in order to take our measurements. And second, what if two identical magnets were stuck together end to end and the experimental procedure was repeated? By adding a second magnet in the same orientation, we'd be doubling the magnitude of the magnetic field produced by our magnets. This in turn would yield larger distances for all measurements. My GlowScript's in the description. Thanks for watching. Bye.